Good afternoon, everyone. So yeah, I'm gonna talk about a covariant approach fractons. I've been working on this for the last couple of years. But first, I should tell you for the third, maybe fourth time, what are fractons? So, well, they are quite recent quasiparticles. The fracton behaviors has been observed maybe around 2005, but the real surge of interest in fractons appeared more around 2017 from the work of Michael Pratkos. And then the physical community has been attracted to fractons, also because they are quite peculiar. Fractons can be found in many different contexts of physics, like spin liquids, generalized electromagnetism, gravity, Witten effect, elasticity, circuits, and so on. And this can be also evident from this nice graphic. So fractons are nearly everywhere. But what's the main characteristic that define all these fractonic particles? That's limited mobility. And in particular, real fractons are completely immobile particles. So they are zero-dimensional objects, while there also exist one-dimensional or two-dimensional objects, so with even, just less restricted mobility, so like sometimes called lineans and planars. But so if one wants to study fractal model, what does it mean to have restricted mobility? So talking to some people, they told me it's about having zero dispersion relation. From a quantum field theoretical point of view, one could think of having trivial propagators, but also some kind of kinetic constraints on the motion, or taking the light cone limit for Carrollian particles. And this also reflects into the fact that there are also many languages that can be used to describe fractons. For instance, lattice gauge theories, which I'm not very familiar with. I'm more familiar with the tensor gauge theories, but in this case, we're talking about exactly solvable spin models, and they are mainly gapped, so I mean massive theories, and they are divided into two main classes called type 1 and type 2 fractons, fracton models that depends on the quasiparticle contents. And then there is also the tensor gauge theories that were mainly developed by Pratkos, which are higher rank gauge theory, which are related to conservation of higher momentum like dipole conservation, and are typically written in terms of rank 2 symmetric gauge fields. These are more gapless model, meaning massless models, and they more looks like Maxwell theories with, for instance, the Hamiltonian is squared plus b squared. So we have some kind of electric and magnetic field, which I will show you in a moment. And the limited mobility in that case is described in terms of a Gauss-like constraint. So fractons can be found in different contexts. For instance, one can use the limited mobility in the context of spin glasses to describe the way of reaching slow thermal equilibrium. They were used in the context of quantum information in order to build robust memories, and this is an example of the X-cube model. And for instance, in that case, we're talking about a spin-like objects, and fractons can be, for instance, identified with these blue cubes and lattice. And why are they fractons? Because they are fractons because they cannot move unless they produce dipole-like objects, meaning these red line operators have the property of flipping the spin, and meaning also changing the color in this picture. And so if one applies this red line operator here, this color changes, and so we get that this blue object moves on the right, but only by producing these dipole-like objects, which only moves on a line on one dimension by subsequently apply this red line operator. So this is nice way of saying that that fractons can only move by producing dipoles, meaning here in this case lineons that moves only on a line. So only by introducing some kind of energy in the model. They are also found in the context of spin liquids when we're talking about higher spin generalization of those models, and all systems which has higher moment conservation, and in particular dipole conservation. And also there is an interesting duality in the context of topological lattice defects, which is usually called the fracton elasticity duality. Now I will be more into my field, so in the gauge theory context, talking about what's a fracton model for instance, Rethko's theories. And here we're talking about a theory which is more Maxwell-like, and in that case, the limited mobility is implemented through a Gauss-like constraint where the electric tensor field is a symmetric field, and so with two derivatives, this equation implies a dipole conservation through an integration over an infinite volume. So this means that single charges cannot move in isolation because they would break the dipole conservation, and while dipoles in this context are completely free to move. So in order to build these kind of theories, one needs some ingredients, and in particular the symmetric rank 2 tensor field, where I and J are space indices. There is a need of a symmetry and the Gauss constraint, so to have the limited mobility, and the Hamiltonian being Maxwell-like, so E squared plus B squared, where the electric and magnetic tensor fields looks like that. And in particular, it appears this A0 field here, which is a Lagrange multiplier, which is implemented into the action in order to give the Gauss constraint. But one can also think of adding other constraints, for instance, a traceless constraint on the electric field, and this gives an additional conservation of a component, which is the trace of the quadrupole moment. This gives us also the other kind of quasiparticles, like the two-dimensional particles. Indeed, while fractons were already immobile in the standard scalar charge case, the additional constraint on the quadrupole moment gives a constraint on the movement of the dipole, meaning that now dipole can only move on a plane which is transverse to its direction. I was mentioning the interesting duality between fractons and elasticity, which is a nice practical example of where one can see fractonic-like behavior, in which the duality involves the electric tensor field and the magnetic vector field related to the strain tensor and the lattice momentum of the theory. And this is a duality that only exists in 3 space-time dimensions. That's because that's the only case in which the magnetic vector field for fractons is a vector, so it can be mapped into the lattice momentum. And in that case, the duality also translates in the particle content, meaning that in that case, fractons can be identified with disclination and dipoles with dislocation, thanks to their property of motion, meaning that the fracton or the disclination can only move by producing a dipole-like object. Like this reminds of the X-cube model I mentioned at the beginning, while dipoles can move on the line, so they're more free to move, like disclination in the lattice. So, however, there are some issues, some strangeness from the quantum field theoretical point of view. One needs many ingredients in the theory, some ad hoc definition, like for instance, this A0 multiplier, which is not related to the rank 2 tensor field. The theory is fully non-covariant. There are an inhomogeneous number of derivatives and some bizarre mass dimensions. So from that, the idea of building a covariant theory for fractons, starting from a symmetry-based technique, meaning that now the idea is to promote the fractonic symmetry to a covariant symmetry, and so from just first principles, like one can do with just standard electromagnetism and Maxwell, one can build the most general invariant action, then identify the equation of motion of the theory, and then see what's the physics of the model. So the idea is to start with the symmetry of the covariant symmetry of fractons, and then analyze what's the most general invariant action, then compute the equations of motion. So in that case, the symmetry, together with covariance, locality, and power counting, are the only ingredients of the model. So just by starting with that, first result is that one lands on this action, which has two free parameters, and it's been ordered this way. One of the two terms is well recognizable, being the term of linearized gravity, which in a sense is an interesting first result, because it was always suspected that fractons were related to linearized gravity, but in that case, gravity comes out naturally just from the symmetry. And in particular, that's because the fractonic covariant symmetry is a particular case of the diffeomorphism symmetry, which is also known as longitudinal diffeomorphism. While the other term here, it's called a priori for the moment fractonic term, it's an additional term. It's also interesting to notice that we can isolate the linearized gravity term by asking for the theory to be invariant under the full diffeomorphism, while for the moment we don't know how to isolate this fractonic term just from symmetry principles. So it seems that fractons comes with linearized gravity. A first interesting thing to analyze from a gauge field theory point of view is the degrees of freedom and the gauge fixing sector. So that's also interesting because one can apply the standard Faddeev-Popov procedure. Looking at the right-hand side of the transformation, we have a scalar gauge parameter, so we need a scalar gauge fixing, but also thinking about linearized gravity, so looking at the left-hand side of this transformation, why not considering a vectorial gauge fixing? We are talking about 4 conditions rather than 1 condition, so 4 is bigger than 1, and so are the results different? What's surprising is that they both give the same number of degrees of freedom, both the scalar gauge fixing and the vectorial one. And even more, the vectorial gauge fixing seems to be preferable because we're not constrained to work into a specific gauge, being the Landau gauge. And also we are allowed to go into the pure linearized gravity limit. Yes? Mm-hmm. No, we are considering still the same action. That's a strange thing, is that we can consider both terms and nothing changes in that case. Yes. I mean, it's this in the end, the equation of motion of the multiplier B.
So B is the multiplier.
Yes, that's the equation. So it's a scalar equation. While this is a vectorial equation, and that's the point. It seems strange.
When you
yeah, that's one. So the most natural would be the first one, right?
But it's not a matter of tidying up the fact that
Yeah.
So how can I?
Well, in a sense, you're looking at this being a vector, probably, like in linearized gravity.
So you
More like that, yeah. Yeah, that comes from linearized gravity thing. So
sure,
that's
that's
it.
what, but it's a different.
Yeah. That's what it seems, but by doing the computation, that in the end you end up. Yeah. Yeah, that is weird. It's not indeed. We don't have different number of degrees of freedom. I mean, we have 6 in both cases. Well, this is 5 because the theory is traceless. With this combination, the theory is traceless. So that's why the 5. Meaning, first class, meaning, sorry. Yeah, I mean, the counting is quickly done in the paper just by looking at the equations of motion, and that's what and you get. Yeah, I mean, by setting this equal to 0.
You pick an arbitrary.
That's for general learning. Lambda is general, you don't have to fix it. Well, maybe we can discuss that on a blackboard. Yes, sure. Yeah, sure. Yeah. One can be obviously reabsorbed by redefinition, but the thing is that we keep them both so we can think of switching one of the two off, so to concentrate on one or the other. So yes. Yes. We're not starting from an algebraic point of view, I mean, but we end up with dipole conservation here too, so that's the point. I mean, starting from this covariant theory, then one ends up exactly with the equations of fracton theory, for instance, Maxwell-like equations of the literature. So that was just another way of starting thinking of a more covariant Maxwell-like theory. Okay, so going on from that, one can think of building indeed a Maxwell-like theory, so like a field strength, an invariant field strength for fractons, starting, we want this to be invariant under the fractonic symmetry, and by just asking this, one lands on this configuration of the field strength, which is also cyclic in the sense and also have a Bianchi-like identity. And what's also interesting is that both action terms can be written in terms of that field strength, and one of the two looks like a Maxwell-like term. So we want to concentrate on that term, so we switch off the G2 term, which is the linearized gravity side, and we want to analyze that. And we study the equations of motion and the Bianchi-like identity one, like one can do with Maxwell theory, for instance. The components of the equations of motion are the Ampere and Gauss law, and then from the Bianchi identity one find the divergence of the magnetic field and the Faraday equation. And the same happens here, in particular, looking at the 0,0 component of this equation of motion, we can identify a particular solution which gives us this scalar A0 field, which reminds of the A0 multiplier of the model. And by keeping this in mind and looking at the rest of the components of equations of motion and Bianchi identity, one lands exactly on higher rank generalization of Maxwell theory, and these also coincide exactly with the equations of motion with the equations of the literature for fractons, for the scalar charge theory of fractons, where the electric and magnetic tensor fields are defined like that and are exactly like a higher rank Maxwell related to the fracton field strength. So it seems that in this covariant theory, the fracton theory of Bredko are embedded in the covariant model through this particular solution. And also one can further analyze the theory by looking at the energy momentum tensor, which looks like a high rank generalization of the Maxwell one. And also one identify the energy density, which is exactly like E squared plus B squared, which makes us constrain the sign of the G1 parameter. Yes? Mm-hmm.
And conclusion in that.
Yeah.
That's another way of saying it is.
Mm-hmm. Yeah, well, so, then we end up, we take the flat limit.
Even
mm-hmm. In the end, that's what we have, yes, through the solution.
So your field content is
yes.
Tensor.
Yeah, and yes, we start from a different theory than the fractons are in that solution. So yes, in that. So
Your map to A0 here.
Yeah, it's a solution of the equation of motion.
Okay. And like if you do couple this.
Yeah, no, that's different. Yeah, that's why the covariant theory is helpful in this sense. Yes. 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 Under the fracton symmetry, the covariant one, yes. Well, I think that comes from the covariant formulation. I mean, everything is written in terms of the covariant field strength, so everything is naturally invariant. Thank you. And, well, what's also interesting by computing this energy momentum tensor is that we can also compute a Lorentz force, a Lorentz-like force, by just introducing a matter coupling in the theory. And this is also a confirmation that we are dealing with with a fractonic theory, in the sense that we can see that the force is acting on the dipoles and not on the scalar charges, which are indeed immobile and they cannot feel the force. Just to summarize up to here, the covariant formulation of fractons from the symmetry principle gives us this action and the equation of motion, from which one can identify results in the literature, and in particular motivate this A0 field as a particular solution, recover the Maxwell-like equation, the energy density and the Lorentz force, and also the computation of the energy momentum tensor, and the strong relation with linearized gravity comes out naturally. One further step that is interesting now that we have a covariant formulation is to study boundary effects on these fracton models. Why are boundary important? Well, there are many examples. The first case that comes to mind is, for instance, the Casimir effect, but also, well, maybe the most notable example comes from topological field theories, which on their own, they are mostly of mathematical interest, having a zero energy momentum tensor and zero Hamiltonian, while adding a boundary in that case gives local observables on the boundary itself. So one can identify a physical content, like, for instance, the two Schwartz type models like Chern-Simons and BF theories, which are related with fractional quantum Hall effect and topological insulators such states. So also in the context of non-topological field theories, ADS-TFT as relation with, for instance, condensed matter theory, together with many other cases, and Maxwell theory with topological insulators. And it seems that also fracton models may have some relation with edge states of higher order topological insulators. In the context of quantum field theory, the first approach of a boundary in QFT was done by Szymanczyk in a more formal context. And the idea was to understand what is a boundary in the QFT and what are the consequences. And in that case, the boundary was a surface that separated the space into two parts. So it was a two-sided boundary. And the consequence in that case was the separability of the propagators, meaning that propagators must be zero for points lying on opposite sides on the boundary. What's the approach in my case is more of a holography without gravity in a sense. And the idea is to consider a one-sided boundary, so the theory is only on one of the two sides of the theory. And since we don't want to introduce anything by hand in the theory, but we still have to impose boundary condition in the system. An idea is to introduce the most general boundary term that was done for the first time by semantic, and well, that's the term that from variational principle can give us the most general boundary condition of the theory. And since we're adding a boundary in the theory, this breaks everything. And for instance, this breaks the symmetry of the theory. Of course, I'm considering here an example of the Chern-Simons case, just because it's easier to show the computations, and with respect to the fractonic case, which I will show you in a moment. So the symmetry and the word identities are broken by the presence of the boundary, by this right-hand side term, which gives us a way to identify the degrees of freedom of the boundary theory by going on shell, meaning switching this j equal to 0 and solving this equation. So this is telling us that on the boundary we are having scalar degrees of freedom. Yes, this is the Chern-Simons case, so that Yeah, that's a different approach. Yeah, but that was just an example. I'm not following its approach. It's only, I'm just taking the boundary term in that case. Yes, yes. Well, then one can, having done all this computation, one can identify the two-dimensional model in that case, which gives us an algebraic structure, which is Kac-Moody algebra. And this makes us identify the central charge of the algebra with the filling factor of the fractional quantum Hall effect, which is a physical quantity. And by asking for these requests, for instance, just power counting invariance on the symmetry, which keeps this unchanged, and by looking at the canonical variables from this algebra and matching the boundary condition with the equations of motion of the most general invariant action, one lands on the two-dimensional Luttinger theory on the boundary, meaning that this theory is describing edge currents that moves on the boundary, and in particular, a chiral boson on the boundary, just from first principles. Yes, this comes from matching the boundary condition, yes. It's just three parameters, yes. This in the end, one has to relate with the microscopic model. It does not predict anything. It's just telling you have chiral boson with some velocities. So what about fractons now? So the idea is to consider the same procedure as before. So take the most general invariant action with flat boundary and take into account the full action term, both with gauge fixing, source term, and the most general semantic boundary term, which is more complicated also because we need to take into account with the fact that here we have another independent gauge field, which is the normal derivative with respect to the boundary. So starting with that model, again, we have a broken Ward identity, from which we can identify, by solving the on-shell equation, the degrees of freedom of the boundary theory, which in this case are traceless rank 2 symmetric tensor field. And also one can compute commutators by taking functional derivatives with respect to the currents. And this is what one lands on, which looks like a Kac-Moody algebra, but it has two derivatives, so it's not, it's different. And one has the same also for the A field. This is for the A tilde field. So what's the three-dimensional theory? We ask again power counting compatibility, invariance under this symmetry, which is the one that keeps this definition invariant. We look for the canonical variables from the commutators and the matching between equation of motion and the boundary condition. And that's the three-dimensional action, which is written in terms of rank 3 field strength, which are traceless, and also have, so it's Maxwell-like term of the two tilde and non-tilde fields and a Chern-Simons-like term. And what is this telling us? What are the equations of motion? Again, from the equations of motion, we can identify two Gauss-like equation, one for each field, and Ampere-like equation, where the Chern-Simons term plays a role of matter. And in particular, the electric tensor field is traceless. So what is this telling us is that we can here identify the traceless scalar charge theory of fractons from the Gauss constraint and the tracelessness condition, which is telling us that the theory is describing dipole that only moves on a line, because here we are into space dimensions. So they have one constraint on the motion due to the quadruple conservation. What about physical interpretation? And also what I mentioned at the beginning, the relation with higher order topological insulators. Well, it seems that we have some connection through the algebra indeed. This looks exactly like the one that was identified in this paper, relating indeed higher order topological insulators with fracton models. And also, what are these higher order topological insulators? They have edge states that moves on the hinges, so they are one-dimensional. So it seems that maybe these objects are the dipoles moving on the line. And also there are interesting relation with the fracton elasticity duality, which is again a three-dimensional fracton theory, which is a three-dimensional theory that's related to fracton models. And there are also similarities with the so-called self-dual massive gravity through this Chern-Simons-like term. But this, I think you will hear more next week from another speaker, which is a collaborator in Dublin. And so just to conclude this, we built a new covariant theory for fractons from first principle that gives us the results of the literature, indeed from first principle of QFT. We get the energy momentum tensor of the theory, and we studied the gauge structure and the degrees of freedom, and the strong relation with linearized gravity comes out naturally. And also by studying the boundary theory and the three-dimensional boundary theory of fractons, we observed a relation with higher order topological insulators through the generalized Kac-Moody algebra that appears on the boundary. And also we observe a Maxwell-Chern-Simons-like term that gives a traceless fracton model. And finally, this also hints towards possible further studies related to elasticity, duality, and maybe self-dual massive gravity. What about the future? Well, first step is analyzing the three-dimensional model from the point of view of fractal elasticity duality, which is also a work in progress. Possible relation with Carroll theories, And also having a Maxwell-like term would be interesting to analyze a non-abelian extension of this theory, so like Young-Mills theory for fractons, and introducing matter into the theory, so like fractonic QED, relation with torsion also between fractons and torsion. We're looking at a theory which has both linearized gravity and an additional term, which maybe comes from a torsional effect and other effects related with linearized gravity and so on. Yeah. I think there is some dipole symmetry. I haven't studied that, but there are some groups that starts from dipole symmetry and in the end lands on this model. Yeah, I think so. Yes. Yeah, there is some dipole symmetry in the end. Yeah, you don't have the charges, yes. Well,
you'll be able to couple.
Yeah, you can couple the theory with some matter source, and that's. Yeah, I mean, it's through the solution, then it breaks that, yes. Yeah. In the end, yeah. No, we're not taking into account any gauge fixing here, so it's completely independent on that. Well, in a sense, it's related to what he was saying. We are not considering matter here, so it will break probably when considering the matter term, which is the real fracton in the end, which is the real thing that does not move. Yeah, yeah, you can add that, and then you. I think so. Yeah. Yeah, I mean, this model is more related to this term, which is the non-linearized gravity term, so that's maybe the difference. I'm not sure I get. Mm-hmm. Are related from the symmetry, but linearized gravity is this term still. Well, fractons is more contained here in this term. Thank you.